When we took pre-calculus, we were asked to find and graph different types of functions using what we know about their end behavior, using things like leading coefficients. And in fact, here in this box, or to start the notes, I've listed all the things that we learned from pre-calculus about things like reducing functions. Let me actually write that here. Reducing functions, to find common factors, to identify things like holes or vertical asymptotes. And so these were all things that we should have had some familiarity with. Now that we've had an opportunity to go and explore first and second derivatives and understand what that means for a function in terms of its behavior, whether it's increasing or decreasing or identifying any type of concavity or inflection points, we're going to put all of that together now, and we're going to try to sketch some pretty accurate graphs, or as accurate as we can, given what we know about the function's characteristics, things like domain restrictions or any possible intercepts and so on. So really, there's nothing new here. We're just pulling together all the things that we've learned so far about functions to try to graph as best as we can a pretty accurate function graph. So let's go ahead and let's try a problem here. We're going to do this first one here. So if you want to pause the video and write these down, you can go ahead and do so. But whenever we are curve sketching, these are some of the things that we want to look out for. So it may not go necessarily in this order, but I want to start identifying some of this key information here. So I've given you this function, and for just the sake of time, I also listed out the derivatives, but these are hopefully things that you would be able to find a little easily just by applying the quotient rule. But let's just go through and identify some key information. So first off, do we see any domain restrictions? Well, that's wherever our function would be undefined. So for our domain restrictions, I can set my denominator equal to 0, so x squared minus 2x plus 1 equal to 0. And I see if I factor that, that's x minus 1 squared. So my domain restriction, we're saying x cannot be equal to 1. So I'm going to actually write that. X cannot be equal to 1, because when x is equal to 1, that means this function is undefined. Graphically, how does that appear? Well, that's a vertical asymptote. Okay, so I know for sure there's going to be a vertical asymptote there. Now, are there any holes? Well, I know that holes only exist when we have a common factor in the numerator and in the denominator. In this case, I don't see an x minus 1 in the numerator, so I don't have to worry about any possible holes. Now, what about the function's end behavior? Well, if it's a polynomial function, you would look at the degree and you would essentially find the limit of the function. But here, we can also apply what we know about the degree of the numerator compared to the degree of the denominator. This is a rational function. So I can say that since n is less than d, I know that my horizontal asymptote is going to be y is equal to 0. Alternatively, you could just find the limit of this function. You could just say, what is the limit as x approaches positive or negative infinity of this function here? And hopefully you would see that it would be y is equal to 0. All right. Before I jump to any calculus stuff, let's see if there's anything else. Were there any intercepts? Well, for an x-intercept, I'm going to set my function equal to 0. So f of x is equal to 0. So 3x minus 2 is equal to 0. X is then equal to 2/3. So my x-intercept would be 2/3, 0. Well, what about a y-intercept? Well, that's when x is equal to 0. So this function evaluated at 0 would just simply be negative 2 in the numerator and then 1 in the denominator. So 0, negative 2 would be my y-intercept. Okay, so I know my box didn't mention anything about that on the left side, but I did mention something about intercepts up here. So definitely make sure we use those. All right. So I think that tells us everything we need in terms of what we had done with our pre-calc. Now let's actually use some calculus and find some, not sure exactly what happened there. Let's use what we know with our calculus to actually find any extrema and inflection points. So we have our derivative, so I'm going to draw my f prime number line. So I'm going to do this here. So I'm going to do my f prime number line. And I'm going to try to find, first off, any critical numbers. Well, what are my critical numbers? Well, it's wherever my derivative is equal to 0 or where it's undefined. Let's start with where it's equal to 0. If I set my derivative here equal to 0, that's negative 3x plus 1 equal to 0. And I don't really care about the denominator. I'm going to multiply both sides by the denominator, so that doesn't really impact anything with where my function would be equal to 0. So I can say that negative 3x is equal to negative 1, x is equal to positive 1/3. So that's one of my critical numbers. X is equal to 1/3. And I'm going to put that on my number line. Where else would I have a critical number? Well, at first glance, I might be tempted to think, oh, well, my derivative is undefined when x is equal to 1. But if we recall, we already stated that 1 is a domain restriction. So we actually can't include that as a critical number. However, I am still going to plot that on my number line because I know that there's a vertical asymptote there at 1. Okay. So with that said, now let's go ahead and do a sign. Let's test the sign of our derivative in these intervals here. So if I choose a number that's less than 1/3, such as 0, I would get positive 1 over a negative 1. So I know that this is going to be negative here. If I try plugging in something between 1/3 and 1, and again, I don't care about the exact value, I just care whether or not it's going to be positive or negative. So if I try something like 2/3, I know that I'm going to get a negative over a negative. So this is actually going to be positive here. And if I try something greater than 1, like for example 2, try plugging in 2, I'm going to get negative over positive, so this is going to be negative here. And what does that mean for us? It means that my function goes from decreasing to increasing to decreasing. So we can keep all of that in mind. All right. Now let me clear this out of the way as now I go to thinking about our second derivative. Oh, actually, before I do the second derivative, I should make sure I understand what implications this has, our f prime number line has in terms of extrema. I know that my behavior intervals, I know where it's decreasing and increasing, but I also know that I'm going to have an extrema at, or relative minimum at x is equal to 1/3. So at 1/3, if I plug in 1/3 into my function, I'm going to get negative 9/4. That's a relative minimum because the function goes from decreasing to increasing there at that critical number, x is equal to 1/3. Now let's try our f double prime number line. So very similar, I'm going to set my second derivative equal to 0, and I see that x is equal to 0 is a possible inflection point. Again, when I set my second derivative, f double prime of x equal to 0, that's essentially just 6x equals 0. So x is equal to 0 is a potential inflection point. But we could also see where the second derivative is undefined. And again, we already know that the only place where this would be undefined is 1, and we already know that there's a vertical asymptote there. So I'm going to, again, indicate that. At 1, I have a vertical asymptote. Now, similar to what we did with the first derivative, we're now going to check the signs of all the values here, and we should hopefully see that this goes from negative to positive, and this is positive. Okay, all I'm doing right now is plugging in numbers into my second derivative to see if the outcome is negative or positive, which means this is concave down, concave up, and concave up. I do see that at 0, my possible inflection point, we did change concavity from concave down to concave up. Therefore, x is equal to 0 is indeed an inflection point. So it's going to change its inflection there, or its concavity there. So this was a lot of work to set everything up, but now I think we're ready to graph. So I'm going to give you a moment to write all this down because we're going to put it all together in a graph. Okay, so with that said, let me zoom in on this so I have a little bit more space to work with. The first thing I like to do is always plot the points that I know for a fact do exist. I know that there is an x-intercept at where was it? At 2/3 0, excuse me. So 2/3 0, so we're somewhere around here. I know there's an x-intercept. I know there's a y-intercept at 0, -2. I also know that there's a vertical asymptote at x is equal to 1. And in terms of points that I know for a fact do exist, that's about it. Now, let's use the end behavior of the function to give us a sense of what's happening. I know that there's a vertical asymptote, and I'm going to do this in green. There's a horizontal asymptote at y equals 0. Now, remember that your function can cross the horizontal asymptote. That is indeed possible. But I know that in this particular case, it cannot. Ask yourself why. How do I know for a fact that this function does not cross the horizontal asymptote here? Well, hopefully you figured out that we only have one x-intercept, meaning there's only one possible place where this function could be crossing the x-axis. So we know that generally the behavior is going to hug this horizontal asymptote. Now, before I start sketching anything in, ask yourself, do I know that its behavior from negative infinity up until 0? And yeah, not only is it decreasing, we know it's decreasing up until 1/3, but it's also going to be concave down until 0. So what that means is I can graph something that looks like this. And I'm trying to sketch as best as I can a function that is concave down and decreasing up until 0. Now, at x is equal to 0, we know that 0, -2 is also an inflection point. We know that it changes concavity there. So it's still going to be decreasing up until positive 1/3, but it's going to start changing concave up. So if I can kind of zoom in on this right here, it's going to still be it's going to concave up but still decreasing, and I don't want it to indicate something like that. And then starting at positive 1/3, I know that I have an inflection point. So now it's going to go concave. It's still going to be concave up, but now the function is increasing as well. And since I have a vertical asymptote, I'm going to continue to graph this. So it's approaching that vertical asymptote here. So as best as I can, I'm showing that it's concave up and that it starts to increase. Now, after the vertical asymptote, I know that it's going to be decreasing but concave up. From here, since we don't have any other defined points, it's probably a good idea to plug in at least one other point. If I just try plugging in 2, for example, into my original function, f of 2, I know would be, let's see, that's 6 minus 2, that's 4 over 4 minus 4 plus 1, so 1. 2, 4 is a point. So again, I'm going to try to graph going through this defined point that I just found. It's going to continue to decrease, but it's going to stay concave up. So it's going to continue to do something that looks like this. It stays concave up, it stays decreasing, it's going to hug that horizontal asymptote, and that there is a pretty decent graph that we were able to sketch given all that we know. So really, this lesson is about putting together all that we were able to figure out from defined points, any domain restrictions, and then using what we know about the first and the second derivative to help us sketch both concavity and where the function may be increasing or decreasing. Check to make sure that all of your extrema and your inflection points are in the right spot. But with that said, go ahead now and I encourage you to try these next couple of problems on your own just to make sure that you're comfortable sketching these functions.